You have it on Canvas. So go to Canvas and you will find it on Canvas. And there you can find that you can sign up for them. It's probably under calendar in Canvas where you can find it. But you see that it is on Canvas, and you will see probably instructions for it on Canvas too. Okay, so what we will do now is to continue with our array antennas. And we now saw the uniform array, and then we have binomial array, and we saw this Shelkonov method to synthesize zeros of patterns. The Dolf-Chebyshev array is then the array that is extremely good because it's between the uniform array and the binomial array. So what the Dolf-Chebyshev have here is that it's designed to have the most narrow main beam for a given side lobe level. And if you think back now again what we said in the beginning, that maybe we should think about this problem as specifying we would like to have this, and actually that someone just determine what these coefficients are for us. And that is actually what's done with this Dolf-Chebyshev, but it's done in an explicit way, but quite a math-heavy way. We will later see that we can reformulate this as an optimization problem, and it's easy to formulate optimization problem, and then we let the computer solve that optimization problem. So the Dolf-Chebyshev here is that you specify now your side lobe levels. And here are examples where the side lobe levels go from -15 dB to -35 dB. So the array factor is normalized to 0 at the main beam. And then, of course, 35 dB down is 35 dB down. And if we see the first one, this is then -15 here. So the one we have here. And if you see what's happening in these cases, if you look at it, you can see the side lobe levels is then the level of these ones. And the main beam is, of course, the one here, which is amplitude 1. And those are now 15 dB down. Between each dashed line, it is 10 dB. So the first greenish dashed line is -10 dB, and you can see the next reddish dashed line is -20, and this is between. And if you look at it, it probably pretty much looks as a uniform array. You cannot see the difference between this one and a uniform array. The only slight difference is that the side lobes are actually exactly the same level of these ones. The uniform array has not exactly the same one. And you can see it also on the coefficients that sits here. So you can see that the coefficients are almost the same amplitude. You can see here, this is basically a uniform array would be a fixed line there. So this is very close to uniform array. And now what we do is that we, of course, push down the side lobe levels. So in the next one, I go to -20 dB. So now you can see that the side lobes here move down one level. So now they are down to 20 dB in these cases. So much, much lower. And in that case, you can also see that what happened with the excitation is that you start getting this tendency now to tapering. So look at the shape of those excitation coefficients. What happened is that you push down the energy on the edge of the array, and you have more relative amplitude in the center of it. And then think back, what did we do before the lecture? Then we have the binomial array, which has really low levels on the side of it and high in the middle, and you have no side lobe levels. So what you play with to push down the side lobe levels is this discontinuity that you go from 0 excitation outside of the array to high excitation. It's a jump. That is what you remove here. And of course, pushing this down further in these cases, now it's -25 dB. You can see the side lobe levels goes down. The tapering gets smoother and smoother. Move a little bit further, -30 dB and -35 dB. And if you look at the 35 dB, it looks pretty much as the binomial array. There is a difference here. There are some side lobes that you have here, but the beam width here is actually more narrow than the corresponding binomial array. So you trade that width of the main beam because you want to have a narrow main beam. And you say, I accept some side lobes. I mean, 35 dB down is pretty low. And this is a really good radiation pattern. Dolb-Chebyshev is really, I mean, almost the best you can get. It's a very, very good radiation pattern. Before we move on this, why do you think it is like this, that we push down the side lobes when we go from this excitation to this excitation? Why is there all of those side lobes when you have this more uniform one, or like a 0, 1, 0? And in this end here, you have something that is more smooth, like up like this. And the first one was more like this. Why is it like that? Why do you have side lobes when you have these discontinuities? And why is it smooth when the excitation coefficients are smooth? Why is it like that? How can we explain it? Thinking what we've done before, how did we determine in all of those cases the array factor or radiation pattern, the radiation vector from the current? The excitation coefficients here, of course, proportional to the current. What did we do? We multiply with this phase factor, and then we integrated or we summed. And that was a Fourier transform. If you do the Fourier transform for this, uniform array, that is to take the Fourier transform for a pulse. The Fourier transform of these ones looks like this. It's the sinc function. All of those elements out here are side lobes. So to smooth down your radiation pattern, you can look at all this exponential. It has a Fourier transform, which is the exponential, this minus x2, the Gaussian function. It's a smooth function. Take the Fourier transform, it's smooth. There's no side lobes. So what you need to break is this sharp discontinuities here. And it's a general thing in antennas. We will see it for reflector antennas. We need to taper the illumination to remove these side lobes. We don't want to have a lot of radiation here and 0 radiation next to it. We want to have a smooth transition between them. And a physical way of understanding this is that these side lobes is where you get constructive and destructive interference. And if you go it smooth, then you're always smoothing out that transition where you can get a lot of radiation and no radiation. So that's why we try to do this tapering. If you have only like 1 point source there and 1 point source there, depending on the distance, you can go in some difference here. If the distance now come out between these two, if this is like m lambda or something, or n lambda over 2, it's destructive interference or constructive interference. But instead, if I have a case where I have little bit radiation here, a little bit more, a little bit more, a little bit less, and then a little bit more, a little bit less, you can never go to those extreme cases where you have totally destructive interference, total constructive interference, and so on. So this is the smoothness that we need. It's a general thing. Don't try to have a lot of discontinuities if you want to, in some ways, remove side lobes. Make it tapered in some ways. It's a tapering effect, that's it. And Dolb-Chebyshev is a perfect trade-off for these cases. So now we can, of course, combine this with beam steering. We do exactly what we did before. Now we just have an amplitude tapering. And on the amplitude tapering, we just multiply the old one, the broadside radiation, with this phase factor. That is what we can do. And for 90 degrees, of course, nothing happens. But at end fire, we get to put the elements that we had before, but we do a phase that is +1, -1, +1. And if we go through here again, you can see this has a really nice performance. You can really go between here where you shoot out your radiation and your side lobe level stays as the side lobe levels. So very, very good pattern synthesis in the Dolb-Chebyshev case that we have here. And I will not go through what sits behind this because it is mathematical. You should just know that this can be done. If you look in Orphanidis, there is just MATLAB scripts that does this. Behind it sits quite a lot of sophisticated math. And it goes down to something that's called Chebyshev polynomials. And it is the properties of this let us decide these good patterns. So it can be done paper and pen analytic, but it takes a few pages, and we don't do it in this course. I will show you the modern way of doing this instead, which is then more general, but it can produce the same results, but we cannot do it by paper and pen anymore. We have to have another understanding of doing these things. So then we can start asking things. When we did the Dolf-Chebyshev, I did all of those examples for lambda over 2 spacing. But an interesting thing is that Dolf-Chebyshev don't care. It's irrelevant what the spacing is. So you can actually do a lot of weird things with this. And one very, very strange thing is that it can be shown here that the directivity is unlimited as the number of elements increases. So if you have a fixed aperture, you just move more and more elements into it, you can actually get higher and higher directivity. The bad thing is that it doesn't work in practice. So in all of those cases, you really require what's called a sub-wavelength element spacing, so not lambda over 2 anymore. And the effect of this is generally going under the name superdirectivity. Sounds good, but unfortunately it doesn't work. And I will explain to you why it doesn't work. So just look at one example here. If you see the patent up here first, this Dolf-Chebyshev patent, doesn't it look beautiful? It looks exactly the same as our previous Dolf-Chebyshev patent. Really nice patent, n elements here. But of course, in these cases, I put 9 elements with a relative element spacing of lambda over 32. So I packed them very, very high. The patent is absolutely beautiful. Good side lobe levels and so on. But then look at one more thing inside of it. What does this mean? It means that my excitation coefficient that I have to compute are those ones there. And you can see that they oscillate now with this 180-degree phase, which we use when we steer a lambda over 2 array. You know, you steer it in end fire from broadside. You have to do 1, 1, minus 1, 1, minus 1. Now we see the same thing with this Dolf-Chebyshev version, that for the previous case was very smooth and nice. Now it's oscillating like crazy. And that is the problem that we have in these cases. If I took the same patent and I do the uniform array here, you can see it is a uniform radiation pattern. So if I space my elements lambda over 32, 9 of them, this is the ray factor I get from a uniform array. And superdirectivity is a term that is used when the directivity is there much larger than for a typical reference antenna. And the typical reference antenna for an array is a uniform array. If your result looks much better than a uniform array, you should be suspicious. Maybe it is superdirective. And if it's superdirective, either you did something totally brilliant, or unfortunately, most likely you did something that's completely wrong. So what are the problems with this superdirectivity? The efficiency of these antennas are usually incredibly low, and the bandwidth is incredibly narrow. So in reality, it doesn't work. And if we see what happens, if we take my nice patent I showed you here, and I can take the Dolf-Chebyshev synthesis, these are the coefficients. These are the one that is plotted here. And first of all, now you should question me. A typical case like I try to avoid and I'm very picky of is that when you write up a lot of big numbers, you know, don't write too many digits. But look at this one. It is, how much is it? 7 million, I think, something. 0.34. The next one here, 0.30, and so on. So obviously here, I mean, otherwise I am a little bit off, or actually I do this for a purpose. I do this for a purpose because the sum of these coefficients is that you would like to have broadside radiation. At the broadside, the radiation factor is the sum of the elements. So the one that sits here, that this goes to 1 there, which is 0 dB, is due to this sum here. So I sum up something that is several millions, and I get 1. Okay, beautiful, I get the radiation pattern. Then you can start asking, what is the power? The power is proportional to the sum of the squares. And what that would be proportional is 10 to the power of 17. So of course, if this would be in watts, you would have 10 to the power of 17 watts. You can do something with that power? What do you think of power from a nuclear power plant is typically? That is 1 gigawatt. This is 8 orders larger than you get from a nuclear power plant. Of course you cannot do it. You could then think I can just lower the power, maybe I can do it. No, you will be killed by losses. It is impossible to do. But mathematically, of course, we can just run Dolch-Chebyshev, we can just synthesize it, we can be happy. But we have to also be realistic that we have missed something in the analysis we have. And here, the analysis we are doing is not valid anymore. It's not valid when we start going to this extreme spacing. The array factor works well for lambda over 2. It works maybe for lambda over 3. But when you start pushing them closer, it doesn't work anymore. And then, of course, we have to do something else. So in all of these cases, of course, the current here is very strong. And as I said, then the ohmic losses is actually proportional to this number in the system. So you will be killed by ohmic losses. You won't radiate anything from this one. It doesn't radiate. And you get all kind of strong effects that actually we haven't covered. So you will have what's called here strong reactive near fields when you do this, which means array factor is not valid anymore because you have a strong mutual coupling and so on. All kind of weird things comes in. And this is, of course, important to be aware of because we learn a tool here. Array factor is really good, but it also has its limitation. Dolch-Chebyshev synthesis is fantastic, but we cannot push it too far. The method will still work, but it will not model reality anymore. So same thing here as an example. You have an a property that the directivity is much better than a uniform array. So if we compare this Dolch-Chebyshev array now for different spacings with a uniform, the uniform is the green color that comes here. So the green one is the uniform and the black one is the Dolch-Chebyshev with this subspacing. And if I do them now first for lambda over 2, I sum the absolute value of the elements is always 1. Perfect. This is your case. So you can see that your Dolch-Chebyshev has almost the same bandwidth, beam width as the uniform, slightly wider, but the side lobe levels is much better. So of course, it's beautiful in some ways. If I start moving up in these ones, so instead we go to lambda over 4, yeah, it probably works. It's not at least impossible to make this work. It's still, you know, almost the same, slightly better. Yeah, it's okay. Slight superdirectivity, but not too much. If you start going to lambda over 8, now you start pushing it. The black one is so much better than the green one, so the black one doesn't change when I change the element spacing. Only the uniform does. If I go to my case of lambda over 16 in these cases, of course it's absurd. If I just sum the elements here, it's not 1, it's 10 to the power of 6. And if I sum the square, of course, it's just losses will kill you in this case. So it's always good to compare to something that's slightly more realistic. And if it's too much better than the realistic, probably it doesn't work in these cases. So this is superdirectivity. And it can be a problem in some numerical optimization of communication systems. If you just plug in that you have some array somewhere, you are not careful of making it realistic with the element spacing and so on, you would like to maximize the capacity, yeah, you can actually come into cases here where you go into superdirectivity. So your solution might find a superdirective solution, which is not realistic. And the only way to really restrict this is to say that you have like lambda over 2 spacing or lambda over 3 spacing, or you include losses in these cases. So you say that the losses has to be below some number, and then actually this will be avoided in these cases. So it's one thing that can happen when you put antennas and you don't think about the real physics of the antennas. That's it. Okay, so now we saw some cases of determining good radiation patterns. So I mean, uniform, our baseline, too high side lobe levels, as you can see, a little bit too high for our flavor. Binomial, really good, but too wide beam. And to have 0 side lobes is too extreme. And of course, Dolch-Chebyshev, we can get it out, we can compute it, people have done it, and you have a perfect trade-off between side lobe levels and beam width. And then you can just asking, I mean, why should we do this by hand? Maybe we should go back to my first question. What would I like my array to do? And then we just ask the computer to give that to me. And actually, this pattern synthesis is really good for these cases. We can solve almost all of those problems very simply in antennas, where then your job or the designer's job is actually more to specify what we would like to have. For example, we can say that I would like to have something that is an array factor, so maximize it in some direction. So like here, you want to have a lot of radiation in this direction. And then you want side lobe levels that's not only below a constant, maybe you would like them to be below a floating constant. Maybe it doesn't have to be constant, there can be shape on it. And in practical cases, there usually is. And of course, you would like to say something about your excitation coefficients, because if you don't do that and you run these cases, yeah, you will very easily go into this super directive mode. But then you can put in your excitation coefficients to be below some number. Okay, and it's easy for us to, in some ways, think on a higher level. Think of what you would like to do, and then try to formulate as a problem that can be solved. So if we do that, we come into a topic here that we will not go through. I will just convince you it is something that's really powerful. Maybe some of you have seen this before. It's not the core of the part to learn this convex optimization, but you should think about how you can formulate a problem in this way to solve them. It's a very powerful way of thinking. And to do that, you only need to know very few things about this optimization. So convex optimization is typically written on this way. So what you would like to do? Now we say minimize some function, should be convex, subject to some constraints, should be convex, or there should be some equalities as it's done. What does it mean that it's convex? It means that it looks like the curve I have to the right. This is typically convex. X to the power of 2 is convex. So as long as our goal looks like that, it's convex. It means in these cases that the red curve here is not convex. The formal definition is that if you draw a line between 2 points, as I have here, then my function has to be below that. If I draw it up there in the red one, you can see here it's above it, so it's not convex. So it cannot have these local valleys or something. That we cannot have. But we don't really dig into this in this course. And what you need to know about this is, of course, it's good if you know something behind it, math and so on, but it's not part of this course. There are other courses. But what you should know is that if something has these properties, you can solve it with efficient standard algorithms. Basically in the same way as you do MATLAB, solve a matrix, put backslash, it's solved. Here you can solve many more things, but you need to formulate it in basically this format. And when you solve it, you don't get trapped in like local minima. Typically you don't, because they don't exist. Of course, there can be problems of doing it, but in general, you don't. And the important factor of this is this one. If you formulate your problem in this way, it's actually solved. You don't have to care about the gritty, nitty details how to do it. It's solved. Which means that when we think about arrays, maybe partly we should think about how do we actually formulate them as good optimization problems that the computer solve for us. Then we jump up one level from this Dolch-Chebyshev, a lot of analytical techniques and so on. We think slightly higher. And that's very important to do in some cases because we can get better results. And in this array and antenna formulation, a good thing is that many problems we have can be formulated as these type of optimization problems in these array factors A, as I had my excitation coefficients, and actually in general in the current. They often behave in this way, which means we can ask this in a structured way in some ways. And if we look in our case here, so what we did for these array factors, what did we have? We have that my array factor here, it depends on the angle theta. It's a one-dimensional array. We will do two dimensionals on Monday. And that means it's just a multiplication here of some known vector, all of these numbers. That is the direction you would like to have the array factor is basically known. You should determine, in these cases, these coefficients. So you should determine the A. F is known. So what would you like to do in these cases? As we said before, you would like to radiate in some direction, not match radiation in other directions, and typically have low coefficients. That's where we started this lecture. This is what we like to do. So how do we formulate this as an optimization problem? And then a thing that comes here is that these things here, for example, radiation, if we take away the absolute value of that, when we say one radiation, that is called a linear term or affine constraint contain, you can do anything. All of these things here measures the size of it, it's called a norm, and you can always have it as a constraint or you can minimize it. Whatever you do, it's always convex. And now we can just start playing around with this and ask the computer to give you your array synthesis for these cases. So let's take the first case, this Shelkonov zero placement method, and let's try to formulate it as one of these optimization problems. So instead of you think like, how do I solve this specific case that I told you to do? You try to do it on a higher level. And now we say that the Shelkonov method was not so good because you didn't have control about your main radiation, for example. And that you can do by, you can say that I would like to maximize here the radiation in a specific direction. Then I would like it to be 0 in other directions. These are still convex constraints. This is a norm that is a convex constraint. This is a convex optimization problem. You can just plug it into a solver and you ask the solver to solve it for you. It actually gives you the answer. For some cases, of course, it's less useful, it's not so useful. A slightly better formulation of the same thing, slightly more stable, is to say that don't specify now it's really, what to say, 0 in all of these directions. Make it as low as possible. So you can say instead that you minimize here the direction, the radiation in all of these directions. You just write up what all of these F are in these directions. You say it should be a main lobe in a theta 0 directions, and your coefficient should still be less than equal to 1 when you sum them. And these are directly solvable problems. We can plug it into a solver. A typical one and the easiest one to use is called CVX. It's free to download. You can just download it from the internet. It runs within MATLAB. And the only thing you specify is precisely what we said we would like to do here. So if I go back to these ones, I say I would like to minimize these ones. That is the norm of these coefficients weighted with this F. I would like it to be 1 in one direction, and I want to have the sum of the coefficients less than 1. And that I can just write in these cases. So here I would like to do something. I would like to minimize the norm of these ones. That is my objective function. These are my constraints. So maximum radiation, the main beam in one direction, and the sum of the array coefficients in absolute value should be less than 1. And the code that runs this is one that sits here. These plots the results that comes out. And that actually basically does everything of this method that we learned to do before. It doesn't say that those are meaningless. Those are really good methods. But of course, we can do more things today because we have also more tools. And these are some of those tools that can be used. So if we plug this in, we can do different versions. This is a different version. Side lobe levels. So think about the Dolb-Chebyshev, all of these polynomials. What the formulation there is that you would like to have, again, a minimum level of the side lobes that sits here. So in a lot of direction theta n, it should be as small as possible. The maximum should be as small as possible. Again, radiate in one direction and have your coefficients less than 1. And the results you can see out here. And again, this is pretty much exactly the same results as you get from Dolb-Chebyshev. And this is a way you can think about those and reformulate them. And the important thing for you is to be able to start thinking like this. Thinking what you would like the system to do. And then let the computer help you of designing it. And here's the same code that does this. You can try it yourself. You can just run these codes. You have to download CVX and install it. And then you can just try to run it. And it actually will produce good results for this case. Okay, so that was some versions of this beam steering and pattern synthesis. Now we'll go over to the next case of this, that so far we've been thinking about a single beam. But in many cases, why would you like to have only a single beam? And is anything we've done restricted to a single beam? Actually, it's not. We can as well add those up and we get the multi-beam array. So if you think you do now Dolch-Chebyshev or you do some optimization, we go back to we have a specific spacing here, lambda over 2. And of course, I can determine the radiation patterns or the coefficients that gives me this Dolch-Chebyshev array in 45 degrees, 90 degrees, 120 degrees. You see them here. And then you ask the question, I would like to have a radiation pattern simultaneously in all of these ones. What do you do with the coefficients? You just add them up. Because the array factor depends linearly on these coefficients. Then afterwards you square it to get the pattern out of it, but there's a linear dependence on these cases. So if I sum them up here, I can at the same time have these patterns where I radiate in all 3 directions at the same time. And now I have a multi-beam array, which of course is useful if you think about communication system. Either you can have different users in different directions, or you have some multipath propagation. So the radiation here hits the wall, go down there. Maybe this one go straight out and this hits a wall there, and then they end up somewhere. So you can do some multipath propagation where the wave propagates in different directions, and then you can ask them to add up afterwards. And that you can do with arrays. So we can have different amplitudes and of course signals in different directions. We can send anything. We can just synthesize the patterns. And if we now say that I would like to send it, so for example, 3 beams, then I had 11 elements in these cases. So what I have to do is just to transmit the signals here. Let's say I have 3 of them in these directions. And that means that my coefficients here can be written as some linear combinations between these signals. And those arrays is just these elements of the Dolch-Chebyshev coefficients. So if I determine them for these specific directions, I can just weight that in and send those signals by in some ways putting each signal on each antenna element. And that makes the thinking for you and the understanding here is that I have now these 11 elements, but I have only these signals 1, 2, 3. So of course I have the first pattern that sits there. And these elements inside of those ones, those 11 elements should of course now just radiate one S signal out there. But it's using in some ways in our array all 11 antenna elements. So the signal is divided on all of these antenna elements, and it gives some amplitude and phase on those ones. And the resulting wave is propagating like that. The same, of course, on these ones and on these ones. And at the end, I get out this radiation pattern here, where one signal can go there, one signal there, one signal there. It can also be that it is the same signal that's added up afterwards in some MIMO systems and so on. We have a huge freedom to do processing on this. Signal processing, how we actually transmit these signals that comes out. And then, of course, you can say, yeah, okay, this was 11 arrays. What do I do if I want more narrow beams? Then you just take an antenna here with more elements. This is a Dolch-Chebyshev with 21 elements. And if you have more elements, you get a more narrow beam. So you can have more, sharp direction where you transmit the signal and the power. And you can do exactly the same thing. And then you start thinking what's happening in 5G and so on. Of course, that is where we go to this massive MIMO type. You go to base station that contains more and more antenna elements. And that gives you larger and larger freedom to control your radiation. You get a more narrow beam if you want to send it, and you get a larger flexibility to resolve different angular parts. So you can send one signal that hits the wall there, and then it bounces somewhere, it goes to the receiver. From the antenna perspective, you don't know if it has to bounce. It is that you can measure the received signal from the transmitter, and they're coming at different time delays. Then you can send them back at different time delays. You can make them add up. You can do a lot of signal processing on that one to get a good communication system. And that we can do, of course, this multi-beam arrays in these cases. And a typical case where this is good, and what happened with this MIMO in some ways when we see the 4th generation of cellular communication. That is that something that was very difficult before suddenly actually become very good and helpful. And one thing with this was fading. Fading has been really the big problem in wireless communication until basically 2000 in some ways. And the reason for that is that you have an interference pattern. If you have one antenna transmitting here, you can see that you can get some received signal here measured with the dB now of the H field in this case to make it simple. And you can see that, okay, down here I receive basically no signal, so bad luck, I didn't receive anything. If you sit out here, you receive a very stable signal. And if you are a person walking here, you always receive the same signal strength. Very good and simple to build a system for this. You know, it's stable, you get the same power all the time, you don't have to deal so much. But if you now put up walls around this, or in a simpler case, I say now that I have 2 transmitters. That is basically the same as you think you had an image theory, you have some reflection in the wall, it looks like there's an image source somewhere. Then this is how the patterns look. So this is again the H field that you want to receive the electromagnetic field. And now if you think you're a user walking here through this environment, these are wavelengths that you can see on the scale here. You can see that sometimes you have a very strong signal here. It's yellow there. Good, strong signal. Very close to it, a few decimeters typically away. Then you sit in a very weak signal here. Then it gets blue. So you have a signal here that's oscillating on like half a wavelength size in some ways. So it's very rapidly going from strong signal to weak signal. And if you only put like one simple antenna in this, like a dipole that sits there, that is the signal it receives. Sometimes very good, move a little bit, really bad. And that is called fading in these cases. So strong signals, weak signals, and it moves around everywhere. Sometimes it's good, sometimes it's bad. And of course, in these cases, I can add more signals, and you can just see it looks more complicated. And that I now have like Hertzian dipoles in free space. It's basically the same if you sit in some indoor environment where you have walls and so on. You have different time delays, you have signals coming from different directions. And the total thing on the field is that it looks like this. Means it looks like a mess. And of course, add more, it just gets more and more messy all the time in these cases. So how do you resolve this? How do you put a good antenna in this environment to actually receive the signal? Then you go back to this multi-beam array. So we take an array instead, because the array can actually resolve the direction from where the signal is coming. It doesn't measure the field in a certain point here. It measures the field that comes from some direction. And then you actually resolve this fading problem, because the signal really looks like it comes from basically one of this, which is a very stable, nice pattern. So we can take this and I can plug in my array. And if I put my multi-beam array inside of this system, I can say, let's just receive one beam to each transmitter, or maybe I don't want to receive it from some, then I can put a null there and so on. So I can really utilize this complex environment, or at least I can use my array to not suffer from it. But I can also utilize it because I can get more and better signals, because I can resolve these things of having transmitters that actually send signals over different paths. And then I can weight up the signal that comes in this one and this one and this one with different complex weights. This takes care of this time delay inside of them, and I can add them up and get a stronger signal. Or I can put different information on this one and so on, and I can get higher capacity. And that is this MIMO way of using antennas, which are array antennas. So arrays are fundamental for these cases. So if we look at the MIMO case, this is what you basically do. You have some base station that sits here, you have some receiver that sits here, and of course antennas don't look like that. They're like integrated in these ones in different ways, and it's very hard to do it at low frequencies, slightly easier in 5G and so on. And you have some signal here that can propagate and bounce somewhere, and somewhere signal can go the straight way. And you just want to use this complex environment, which is where you need arrays for these cases. And if you don't do this in array, you need to write up, how do I connect my transmitter and the receiver? Many of you will see this. You have a course in all of this case. And in antennas, we need to see it from the perspective of the antenna in some ways. So for the antenna, we have a transmitter and we have a receiver. In all of this, we have some different antenna elements. So you have an array with different elements. One is the transmitter, one is the receiver, and somehow you will have a connection between the received signal out here in the receiver to the transmitted signal that sits there. And the good thing that we know one part of it is that we have linearity here. So there is some channel between those that just multiplies the signal you transmit and you get the signal you receive. And that is giving that it excites some coefficient in your array, there is some propagation, there is an antenna and so on. And all of this can be described in this simple matrix type model. And then of course, all of these elements talk to each other. So if I transmit from the first element, I also receive it in the second element and so on. I have a complicated connection between them. It doesn't have to be free space. It can propagate in something very, very complicated environment. And to divide it and get what is good in these cases, you can diagonalize your matrix. So mathematically in these ways, we can say that instead of having this complicated one, we actually have something very simple here. So I shouldn't throw it like that. We have something basically only like this. So straight channels. So now I only have some coefficients that really sits there. And say how strong channels do I have from my transmitter to my receiver. And of course, to do this, I need arrays on the transmitter, I need arrays at the array at the receiver. Sometimes you can have it only on one side, you can still gain quite a lot. And yeah, in these cases, we of course get the weight that comes in. So the transmitted matrix in these cases is what I get from this SVD of my channel matrix. And I had some decomposition into this SVD. And that is what I transmit in these cases are these X signals, which is my multi-beam array. So these MIMOs are really multi-beam arrays, where you really transmit signals in different directions. And you do it in a very complicated environment. And the same way in these receiver settings, you again have that the really received signals here is of course that you have done this diagonalization. It's very simple. And then in physics, it comes down to different signals in different antenna elements. So that's very quickly about some of this MIMO system that sits there. And then we can ask the question here, what is good with different antennas? So now we go back to the antenna perspective of this. So we say that you have your, phone or any antenna you have. What kind of antennas would I like to have in these ones to actually work well in these kind of environments? How should I make them look? How should I characterize what is good and what is bad in some ways? So now if I have many antenna ports in these ones, how should I say that this is a good configuration, that is a bad configuration, for example? And one way to quantify at least partly of these things is to look how similar radiation patterns are. So if we say we have some far fields here, so this is not the radiation vector, it's really the total far field. So in the previous notation, maybe it's also this orthogonal part that sits inside. And then I can say, how similar are these? And then we just measure their similarity. That's called the correlation between them. So if you have one radiation pattern and you have another radiation pattern, you multiply them. And you multiply them, of course, over the entire sphere. And then you have to weight it over the sphere. So you integrate this with this again, sine theta d theta d phi. And then you say they are similar or they are different. And by normalizing with their own amplitudes, as down here, you get what's called this correlation factors for them. And if you put in one element, of course, you get always one. So this rho 1, 1 is always one. And the next one is, of course, less than one. And you would like them to be basically orthogonal or as dissimilar as possible, at least mainly different in some ways. And in a real case, you can have some channels that give some weights and so on, but we don't bring up that in this course. I will just show you one example for this one before we end. So if we say that we have now two dipoles, so think that you have two dipole antennas, half wavelengths dipoles. probably Hertzian as a driven there, but it doesn't really matter. If you now put them somewhere here, when are they correlated and when is the correlation low for these ones? So if I think I take two dipoles, and if I just move them closer and closer, what does that mean? It means this one radiate one donut, this one radiate one donut, and if I put them close together, they basically radiate exactly the same pattern. So if I put two dipoles very closely like this, they are highly correlated, and they don't work well in a MIMO system. If I put them further away, so I start separating these ones, doesn't even have to be much greater than lambda, like half a wavelength or something apart from each other, they start seeing a different world. They still have a donut pattern as radiation pattern, but the phase starts to be different. And when we look at this previous one with the cases here, the phases actually comes in these similarities of the radiation pattern. So when they move away, the radiation patterns are the same, but the correlation is actually starting to get low. So then you can have in some ways, a decorrelated one. And another version is that you take your dipoles and then you just twist one. So you have one antenna radiate like this dipole, you have the next one radiate like this. They receive and transmit different signals, which means they have lower correlation. And that's what you typically would like to have if you think in a case like these small ones. They should see a different world. You don't know if you hold your phone like this or like this or like this. So you cannot say it should be strongly vertical, it should only be in a horizontal plane, because you don't know where the user puts it. Your user puts it randomly. But let the antennas radiate with different patterns. Then they see different worlds. And on average, they will totally receive different signals. And then they can work in a MIMO systems. So they can be like in the ZX, or of course, both could be horizontal. There's still low correlation between them. And that is one way to push it back to looking at what the antennas should be in these array systems to make it actually work well. They need to be sufficiently different in their radiation. And that is the correlation measure between the patterns. So that was quite a lot about array antennas and how we do the pattern synthesis of array antennas. And we will continue with that next week on Monday. So we will continue mainly on array design. I hope I can also talk a little bit about MIMO, which is, about method of moments, which is what sits behind all of the simulations you are doing this week with your patch antenna. What it's actually doing, what's happening in this case. I should also say that this quiz is closing today. I'm not sure what time. Make sure you have done these quizzes before Thursday. The fourth one is open, to my knowledge. It should open already at lunch today. You can see the times on the homepage. And again, there, if there is any problem with the quiz, send me an email. I might have some problems with some of the questions because we moved them from one system to another system. I do try to check them, but sometimes I miss something. And if there is something, don't get angry at the computer. Don't get angry at me. Send me an email instead, and I will fix it. So that's no problem there. And then, of course, we will go into more of the array synthesis. We did basically MIMO already today, so it should said 2D arrays there instead, and that we will do on Monday instead. And the important part for you, the second lab session that starts next week. So sign up for that. Make sure that you in the lab group sign up to the same time. You need to be in the same group. So decide first which one you can go to and then sign up for that. And the group who is 3, of course, need to sign up to one that has 3 slots. And we will try to finish it with the one who is a single one that can add up to the same one. Hopefully that will work. And for the lab, you have also one quiz that you have to do. So there is a specific quiz. It's not open yet. It will open now, probably on Friday or in the weekend, that you have to do before the lab. And that goes through some of the basic knowledge that you should really have when you come to the lab. So don't only go through the quiz and make sure you passed it. Make sure you understand all the questions in that quiz, because that you need to have with you when you go to that the lab, because that is what you're going to basically do in that lab. You're going to learn quite a lot there. And before that, of course, you need to have some knowledge before. And it is mandatory to do that quiz before the lab. Okay, so that was a lot for today.